All right. Good morning, everybody. My name is Burrell. I'm with Samtec. I'll be talking about the next wave of high-speed fabrics, and hopefully what you'll get by this presentation is what's coming on the horizon and some of the impacts on system design. All right, so we'll discuss some industry trends driving technology, next wave of high-speed standards, impact on system design, innovations in interconnect technology, and some takeaways. So some trends driving technology. So data growth is driving technology. There's a critical business need. Data has to be processed quickly. The value of data decreases over time. Data-intensive workloads, advances in AI, machine learning, machine vision are actually fueling growth. Embedded compute power, so Moore's Law, multi-core processors, power management schemes are really improving performance per watt. You've got new devices, FPGAs, GPUs, fabric-attached storage, flash SSDs over PCI. All these things are actually requiring a lot of compute power and high-speed fabrics. There's some new memory technologies that are out and on the horizon. Phase change memory. Intel and Micron came out with 3D XPoint. It's a transistorless type technology, and that's going to migrate into storage and into DDR. And then you've got the traditional PCI Express, you've got Ethernet, you've got OIF, and then you've got two new emerging fabrics, C6 and Gen Z, which are emerging to be low latency IOs. So one thing we have to talk about, and that's the von Neumann bottleneck. So Moore's Law, compute power has really excelled, and the memory technology has not really kept pace. And so what you have is you have bottlenecks in your systems. And so there's two technologies that are coming about right now that are really trying to address this particular problem, and we'll talk about those next. So next wave, so you got two C6 and Gen Z. So by now, probably most people in the room have heard of these. C6 is a cache coherent interconnect for accelerators, and basically what that's trying to do is share memory natively between accelerators and processors, just like a multi-core processor would share cache or system memory. And so the motivation here is to provide a low latency fabric and to provide an open and standardized solution. So down on the table here, we have C6 physical layer is pretty much PCI Express. Gen Z is basically IEEE PHY. Topologies are peer-to-peer and switched. Signal rates for C6 are PCIe Gen 4, 20 gigatransfers per second and 25 gigatransfers per second. Gen Z is PCIe Gen 4 speed and 25 gigatransfers per second. The mechanicals for C6 are going to be straight up PCI Express, and then Gen Z has a new standard that I think they just finished up this past year in small form factor, TA 1002. C6, like I said, is fully coherent, and Gen Z is not fully coherent, but it supports coherent protocols. So some feature highlights for C6. So it's tightly coupled interface between processors, accelerators, and memory. It's an in-the-box solution, so it's not a box-to-box. It's strictly inside the box, and it's backwards compatible with PCI Express. So over in the top right-hand corner, that's basically a C6 to attach memory, and then the other protocols or configurations. Basically, any information you want to know about C6, there's good information on the websites. Use cases allows latency extension of main memory, low latency extension, and it extends cache coherency. So the current file layer roadmap is PCI Express, extended data rate 20 gig and 25 gig. PCI Express 5.0 is next, and then the future is 56 gig PAM4. Gen Z, this one's more of a general purpose, kind of goes head to head with PCI Express. It's scalable, direct attached switched fabric technologies. It can also provide a gateway to other networks, multiple link widths, and simplifies data access to memory operations. Use cases, general purpose I/O, fabric attached persistent memory, node to node, and single node configurations. So its file layer is basically right now PCI Express Gen 4, and then also a 25 gig is IEEE based channel. Next is 50 to 56 gig PAM4, PCIe Gen 5, and then the future is 110 gig PAM4. Evolving standards, so these are your traditional channels and working groups. Right now is Common Electrical Interface 4 for OIF. Right now there's 2 draft specs for 5. There's a 112 gig NRZ, CNRZ, PAM4 channels. Ethernet, they just finished up 802.3 CD end of last year. It provides a 50 gig to 200 gigabits per second PAM4. And right now, 802.3 CK excuse me, is currently underway. PCI Express, Gen 4 finished up last year. And then Gen 5 is actually pretty far along. Okay, so impact on system design. So as we get down the road here with the faster fabrics, signal integrity is going to matter. All your details in your channel will matter. Simulation, basically one thing you can think about is most channels basically, so for instance, a PCI Express link would have a CHEM connector that it's supposed to go through. But not all systems have PCI Express over a basic edge card. So some things you have to do is simulate the entire channel. Routing, so use microvias, VN pads, back drilling, break out traces over layers that have short stubs. So the example on the right there, that's what you would not do. So that routing is, it would come in off the top layer, it would come down to another layer, and it would leave a huge stub that would radiate. Other recommendation, optimize trace impedance to a connector and not necessarily the protocol. So new constraints as FR4 becomes prohibitive. So basically the yellow graph here shows FR4, and we have 2 points in frequency, Nyquist frequencies. We have 16 gigabits and 28 gigabits. And what you see here on the Y column is, let's see. Yeah, so basically 2 things here. One thing is PCB materials are trending to a very low loss dielectric. And then also the thermal characteristics really impact your impedance as you get higher in frequency. So what you see here is traditional FR4, and this would be basically 16 gigabits Nyquist. And you see that we're at about 28 dB, which eats up most of your channel budget. So as you see, there's some lower loss materials that you're going to have to use to enable these channels in the future. Next thing is high-speed cabling. So high-speed cabling is trending to like ultra-thin gauge cable and low loss dielectrics. That requires a sophisticated manufacturing process. The cool thing about cables is there's multiple termination options, and it has superior SI performance over most PCB materials. So here's some innovations. One thing the Samtec is doing is foam fluorinated ethylene propylene versus traditional solid dielectrics, and what that does is it impregnates air pockets into the dielectric, which reduces the dielectric losses. Next up is some sophisticated manufacturing processes like co-extrusion of dielectrics and conductors. And that reduces loss by allowing a tightly coupled channel and eliminates differential skew. And then the third is direct attached cabling to the connector. and that helps reduce impedance mismatches. Here's an example of a flyover system. So basically, data flies over lossy PCB material. In this example, we have our Firefly. And the cool thing about it is the footprint is, or the copper and optical interconnects are interchangeable. And then there's multiple high-density rugged N2 options. There's an extended temperature Firefly for optical, and it supports PCI Express. And what you'll see on the right-hand side here is a VCU 118 dev kit with a VITA 57.1 interconnect looped back with a Firefly. All right, so connector trends. So one thing we're getting at Samtec is we're getting a request for high pin count, very tight pitch, a lot of pins in the connector, and it's still expecting a lot of performance. So when you get something that tight, when you get pins that close grouped together, you have an issue. You can have issues with crosstalk, so you have to really consider that when you're designing connectors. Some things we're doing here are surface mount, and what that does is the surface mount actually reduces or eliminates the stub that you would get with a through hole or a press fit design. The surface mount also eases the breakout region optimization, and it has an added benefit of self-aligning during the reflow. Increased contactor white combined with narrow contact edge also helps to minimize broadside coupling, and it also improves impedance continuity. So an example here would be an open pin field Accelerate HD. It's an open pin field up to 260 positions, 2.2 millimeter row-to-row pitch, 0.63 millimeter pin pitch, 2 different stack heights. This connector is Gen 5 and Ethernet 56 PAM4 capable. So what does the increased row-to-row spacing help with? So the distance actually helps reduce the crosstalk. It also allows for more ground vias to help with crosstalk. And it also, adding those two things also helps with your signal to ground ratio, so you get a real dense channel. And then it eases differential routing. All right, so basically summary here is an explosion in the growth of data is fueled by like data center, AI, autonomous systems. A new wave of generation of fabrics is being developed to standardize the process. These next generations are promising incredible performance, but signal integrity matters. So there'll be a close attention to PCB design, routing, breakout region, and these next gen fabrics and the technologies they will enable will have a huge impact on the embedded market.